as the session chair. So we have 4 great talks in this session, all related to machine learning acceleration. So the first speaker couldn't actually be here in person, so we have a recording that we will be playing. So the first paper is Cambricon-D, full network differential acceleration for diffusion models. So we can go ahead and play the recording.
Good afternoon, everyone. I am Kongwei Hao from the Institute of Computing Technology, Chinese Academy of Sciences. I'm here to present to you Cambricon-D, full network differential acceleration for diffusion models. Diffusion models have many applications. For images, it can perform image generation, super resolution, inpainting, etc. It can also perform text-to-speech and video generation, and more. To give you a quick rundown on diffusion models, it consists of a forward diffusion process for training and a backward denoising process for inference. The forward process synthesizes training data from known images by gradually adding noise. The inference, backward process would then be a gradual denoising model. Here we focus on the inference. We work from a complete noise on the right and run the same neural nets multiple times, each time denoising the image by a bit. Finally, we get the generated image on the left. This denoising is done by a backbone neural net. In images, it's usually a convolutional net, like this one shown here. The network takes in an image like here, image T, and predicts a noise like this one shown here. And we remove the noise to get one step of denoising. Observe that the images are similar over time steps, and the difference, the predicted noise, is small. Thus, the backbone network gets similar inputs each time. One can guess that maybe similar input images would lead to similar activation maps too. The answer is yes. Here we plot the distribution of values in the activation tensors, with and without taking the difference between the two time steps. As you can see, the raw values on the left are numerically large and spread out and has a high entropy. The delta values on the right are small and concentrated and has a lower entropy. This implies that the computation is informationally redundant across time steps. What do we do about this? Consider this math quiz. Suppose I tell you that 1887 times 3 is 5661. Then how do you calculate 1889 times 3? Well, you notice that 1889 is similar to 1887, so you take the difference between the two, which is 2, and multiply 2 by the other fixed operand, 3. Adding this back to the known 5661, you would get 5667, and you get the answer quickly. Applying this to convolution in diffusion, we know that the convolutional results of the previous time step, so we can subtract this time step's activation from the previous one to get the deltas, and perform convolution on the delta input, which critically requires low bit width and is quote-unquote easy. We finally add this to the known output for the convolutional output. In fact, Diffie from Micro 18 has proposed a similar method for pixel-to-pixel tasks, and in their case, exploiting spatial continuity. Problem solved, or is it? As you can see, differential computing indeed cut compute costs by 3.3 times due to the lower bit width, but it also caused memory traffic to bloat by a factor of 5.78. The whole thing is overall slower by 23.4%. The issue is in non-linearities, such as ReLU. They are essential to neural nets and occur frequently, but differential computing demands that the operator be linear to function correctly. They are only correct for linear operators such as conv, but not non-linear ones such as ReLU. So we must transition to raw values temporarily when we run into a non-linearity and compute it using the raw values and then transition back. So in this data flow, to compute a convolutional layer, we first fetch the weight. Then we need to transition the input activations. We fetch the raw input from the last time step, subtract it from the current raw input on chip to get the delta. And we write back the current raw input for maintenance. Then we perform the convolution on the delta. And then we transition again, this time in the other direction, from delta to raw activations to prepare for the ReLU. And then we compute the ReLU and finish. These two transitions are expensive because activation maps are accessed twice in each transition. So if only we could compute ReLU on deltas and use deltas all the way. Well, the ReLU function is defined as so. To allow deltas to pass through them, observe that the ReLU function can be written as masking x using x's sign. The x bar itself is linear and can be in delta, but x's sign isn't linear. In other words, we can compute ReLU on deltas if we knew the sign bits of the raw values. But critically, the sign bit is only 1 bit per value. We can just fetch these signs from off-chip, and it would be cheap to do so, and mask the delta values using these signs. Thus, we propose the novel full network differential data flow, the sign mask data flow. Still, first we fetch the weights. Then we perform convolution directly on chip because deltas are from the last layer and are on chip. And now we fetch only the signs of the last time step, and then compute ReLU as an element-wise AND operation. We then write back the deltas to off-chip for maintaining these sign bits. Note that only deltas are used throughout the whole network. So expensive transitions are replaced with simply fetching the small sign bits and writing back the deltas for maintaining them. So how do we take advantage of differential computing? A naive way is to just remove the leading zeros, like so. But in practice, this doesn't work. We lost up to 44% of model precision, even using a relatively modest int5 width. The issue is in the long tail nature of the deltas. As concentrated as they are on the right, there are still 1.86% of outliers who fall outside of the representable range of the lower bit width, and these matter. Clipping them led to the precision loss we mentioned. A straightforward solution is the traditional outlier-aware architectures, such as OLXL from ISCA'18, with wider outliers routed to the wider multipliers and narrower inliers routed to the narrower multipliers. Unfortunately, they require a complicated outlier routing, leading to compute area overhead, defeating the purpose of saving compute in the first place. And also, outlier and inlier processors can be at different pacing as they fluctuate when dealing with real inputs, causing a synchronization overhead where one size might have to wait for the other, and this happens 70% of the time in our experiments. So we propose an outlier-limited PE architecture. For every contiguous group of n inputs, we allow outliers, but only m of them. They get the wider FP16 multipliers. Anything more than that would be clipped, but this is very rare. This would allow for a more local routing of outliers to save on compute area, and also forces lockstep operation between the inlier and outlier resources, eliminating the weighting overhead. We then propose the Cambricon-D architecture as shown here. Its operation would start with reading the weights from the off-chip DRAM, then loading the delta activations from the last layer from on-chip. The PE would then calculate the tensor operation and buffer it into the output buffer. This then gets sent to the SFU, which deals with the ReLU using the sign bit mask from the off-chip DRAM. This delta output will also be compressed and sent to the DRAM for maintaining the sign bits using a near data processing module. The PE is a SIMD-style inner product multiplier. The main part of it is the inlier segment, where FP16 activations would be quantized and multiplied using narrow FP and int3 multipliers. These activations that overflow the quantization would be sent to the outlier segment, where they would be disparsed and dealt with using wider FP to FP multipliers. Maintaining the sign bits would require maintaining the raw activation values as well. So a naive way to do this is just to fetch the activation to be updated from off-chip, add the delta to it, and write back. We then copy the topmost bit, the sign bit, in a separate contiguous location. However, this increases memory traffic for the fetching and the write back. So instead, we do this on the memory side by embedding a near data processing unit on the DRAM. The chip sends the deltas off-chip, and the NDP unit handles the update off-chip. The NDP unit is attached to the memory buffer. following the design of TensorDim from Micro 19 and our previous work, Cambricon-Q in ISCA'21. The deltas it receives is in a compressed format to reduce memory load, where inliers are stored as a load bit array and outliers are stored separately. The combined effect of all these approximations drops the model precision by 0 to 4%, which is lower than int8 quantization. As you can see, the image quality is maintained. Under this quality, Cambricon-D, the orange bar, achieves 146 to 238% speedup on various models over the baseline in blue. If the old per operator data flow is used instead, the gray bar is shown here. Performance is 60 to 103%, which is usually a slowdown due to the additional memory overhead. Our novel data flow eliminates this. Also, to show the value of our novel PE, if we use a traditional outlier-aware PE shown in green, then only 100 to 209% of speedup can be achieved. The old data flow has a slowdown despite compute acceleration, as we measured 2.27 times to 10.58 times more memory traffic in them. This traffic causes the slowdown. Our methods can get the same compute acceleration while reducing that bloated memory traffic by a factor of 2.92 to 5.68. Our acceleration also allowed us to achieve an energy saving of 25.8 to 42.2%. In conclusion, we observed that diffusion models perform redundant computation across time steps as their input data is very similar. We discovered that differential computation can be a promising solution, if not for a problem. The problem is that nonlinearities forces us to transition our delta activations to and from the original raw activations, fragmenting the differential computing process in a per-operator way. Such transitions are expensive in memory traffic. We solved the problem by mainly loading one-bit signs and passing through the nonlinearities still in deltas. This allowed us to achieve 1.46 to 2.38 times speed up. Thank you everyone for your attention, and I would be glad to receive your questions.
So the speaker is available on Zoom for questions. If anybody has questions, again, please walk over here and just state your affiliation and ask. If not, let me ask a quick question. So thank you for your talk. I was curious if some of the techniques you presented would also apply to just conventional, like convolutional neural networks or even transformers.
You mean which kind of transformers?
Like in general, I mean, is this very specific to just diffusion models, or would some of the non-linearity, acceleration, and like some of the techniques you described also work for other models?
The diffusion computing process should be applicable to any neural nets that has input similarities or continuity in some dimension.
Got it. That makes sense.
So, okay.
Got it. Thank you. Are there any other questions? If not, let's thank the speaker once again.
Thank you for your attention.
Thank you. So we will move on to the second talk. Can come ahead. So next up we have Shiryu Pan, who's a first-year PhD student from Peking University. He's advised by Dr. Zhang. His research interests are in storage systems, near data processing, and machine learning systems. And he'll be presenting some exciting work on federated learning aggregation called Flagger. So go ahead. Thank you.
Thank you. Okay, so good afternoon, everyone. I am Shiryu Pan from Peking University. Today, I'm very pleased to share our work, Flagger, Cooperative Acceleration for Large-Scale Cross-Silo Federated Learning Aggregation. And so to begin with, let's talk about what is federated learning and why do we need it. Nowadays, training machine learning models increasingly relies on a large amount of high-quality data. However, these data are usually geographically distributed among different locations, such as government, hospitals, and banks, which are called data silos. Due to the escalating privacy concerns, strict restrictions are enforced on data sharing, and that's what federated learning is trying to address. So how does federated learning work? To begin with, let's assume that there are several hospitals or clients which cannot share their data with others, but they want to train a model together with all their data. So each of them will train a local model with their own data. After an iteration of training, each client will encrypt the intermediary results, such as model gradients, and upload them to a third-party central aggregator. The aggregator will collect all the encrypted model gradients and aggregate them into global model gradients. After that, each client will download the model gradients and encrypt them. Finally, each client will update the model with the global model gradients and begin a new iteration of training until the model converges. There are multiple privacy-preserving techniques for federated learning, but in this work, we focus on pair-based homomorphic encryption since it is widely deployed with balanced security, model usability, and performance. The pair-based algorithm allows direct additive and scalar multiplicative operation on the encrypted data. However, it will introduce 2 to 3 orders of computation and storage overheads compared with the plain text computation. Several works have been proposed to address these overheads. However, they mainly focus on the client-side overheads. As federated learning scales up to accommodate larger models and more clients, we observe that the aggregation process becomes a major performance bottleneck in the end-to-end FL training. Therefore, we evaluated the conventional CPU-centric aggregator with an FPGA accelerator for FL. The figure shows the end-to-end training breakdown for the baseline aggregator. We observe that the aggregation overheads costs 83% on average during the FL training, and the network transfer alone takes 30% on average. This is because the clients communicate with the aggregator through wide area network like internet, which is much slower than the LAN transmission within a data center. Furthermore, we also evaluated the time breakdown for the FL aggregator. We found that although an FPGA accelerator has been applied, the complex homomorphic computation still causes 46% of time. And as you have noticed, to accomplish the FL aggregation task, computation, storage, and data transmission involves multiple hardware units. These hardware units necessitate the data to be transferred back and forth among these units, which further extends the aggregation time. We conclude that employing only one accelerator cannot address these architectural inefficiencies at once. So what about near data processing? Let's talk about some background of near data processing, or NDP. Compared with the traditional architecture, NDP moves computation to where data reserve instead of fetching data to the computing unit. There are many kinds of NDP devices, and one of the representative is the data processing unit, or DPU, which is also known as the SmartNIC. However, leveraging DPU cannot accelerate FL aggregation because the memory capacity of DPU is too limited to accommodate all the inflated ciphertexts. And another type of NDP accelerator is computation storage drive, or CSD. Although CSD has large capacities flash chips to store all the model gradients, however, only using CSD to accelerate FL aggregation is not a good idea either, because its limited computing power is not sufficient for computation. We observe that the pros and cons of DPU and CSD seem to be complementary, so can we utilize both of them to accelerate FL aggregation? Based on this observation, we propose Flagger, which combines both DPU and CSD as a whole in the aggregator to cooperatively accelerate a shared target, FL aggregation. The computation can be dynamically moved between DPU and CSD during runtime based on the real-time load, and the ciphertext can be directly transferred between DPU and CSD without interference from the host. Okay, so let me show you the overall architecture of Flagger. First, we build a Flagger DPU, which communicates with the client, transmitting and processing ciphertext through the network stack. And then we build a Flagger CSD, which looks similar to the Flagger DPU, but store the ciphertext in the flash chips and perform in-storage aggregation. On the host side, a software-based Flagger runtime controls both Flagger DPU and Flagger CSD to coordinate their activities. The ciphertexts are transmitted between Flagger CSD and DPU through peer-to-peer DMA, which bypasses the host memory and eliminates the unnecessary data copies. Nevertheless, we still face a critical issue. How could we unify and leverage these two distinct accelerators for a shared workload? Since our final goal is to sum up the homomorphically encrypted ciphertext, we choose the widely adopted Montgomery multiplication algorithm, or MONTMOL for short. Here, we don't dive into the algorithm details, and we only focus on how it works for FL aggregation. For example, if we want to aggregate 4 ciphertexts, C1 to C4, we need 3 steps. enter the Montgomery space for each ciphertext, sum them up, and exit the Montgomery space. Through the 3 steps, we can finish the whole aggregation process. Based on this, we made the following observations. First, the first and third steps are actually, they don't have any inner data dependencies and can be performed asynchronously, while the second step needs all the ciphertext to be ready and must be performed synchronously. Therefore, we conclude that the first and third steps are actually pre- and post-processing of data, which can be done on the DPU online. And the second step needs to be performed with large data volume, and they need to be performed on the CSD offline. So we can split the FL aggregation process into 3 phases, amortize and distribute them to both Flagger DPU and Flagger CSD for acceleration. Based on the multimodal engine, we built Flagger DPU and Flagger CSD. First, let's check how Flagger DPU works. It features a network processing capability to perform pre- and post-processing computations. Flagger DPU contains a hardware-based network infrastructure to eliminate the need of the hot-side network stack, which enables Flagger DPU to directly perform in-network processing and prepare all the data for DMA transmission with Flagger CSD. For more network-centric optimizations, please see the paper. The processing unit extracts TCP IP packets for the ciphertext and their metadata, and the multimodal engine is here to make ciphertext enter or exit the Montgomery space. Furthermore, to communicate and keep connections with the FL clients, we need a management unit on the Flagger DPU to perform control plane tasks. It monitors the runtime loads and schedules tasks in the processing unit. Therefore, although through the in-network pre- and post-processing, the lengthy wide area network transmission can be overlapped with more than half of the aggregation computation, which efficiently accelerated the overall aggregation process. Similarly, we have built the Flagger CSD to store large volume of encrypted multi-gradients and perform in-storage aggregation. Flagger CSD also employs a lightweight processing unit, which is similar to that in the Flagger DPU, but is equipped with less multimodal operands. Since both Flagger DPU and CSD employ the same multimodal operands, we could partially offload computation tasks between Flagger DPU and CSD to each other based on their real-time loads. To further reduce the management overhead, we replaced the LBA to PBA mapping in the traditional flash translation layer with a ciphertext ID to PBA mapping. Therefore, the Flagger CSD can directly obtain the metadata of ciphertext without host-side file system and eliminate the interference from the host. For more design details, please see our paper. We implemented and deployed Flagger in a real system. We leveraged the Xilinx Alvia FPG accelerator card for Flagger DPU and deployed 40 multimodal operands. For the Flagger CSD, we leveraged the DC Plus OpenSSD and it deployed 8 multimodal operands. The Flagger runtime is constructed from Xilinx runtime UNVMe lib and the FATE framework. We also choose multiple widely used machine learning models to verify Flagger. And we set up 4 sets of baselines for evaluation, including the traditional CPU-based aggregator platform, the aggregator with a single accelerator with only Flagger CSD, and with both Flagger DPU and CSD, but no dynamic offloading. And we could see that compared with the baseline CPU-centric aggregator, Flagger achieves up to more than 6 times speed up. And we also compile Flagger with other state-of-the-art accelerators. So to conclude this paper, we observed that the aggregation process had become a major bottleneck in cross-silo federated learning due to the multiple architectural inefficiencies. To address this, Flagger combines both DPU and CSC as 2 NDP accelerators for FL aggregation. Compared with the conventional CPU-centric aggregator, Flagger achieves up to 6 times of aggregation speed up. So that's all. Thanks for your attention, and I'm very happy to take any questions.
Again, maybe I'll start with the question. So great talk. I was curious, how large was the system that you evaluated? Maybe I missed that. Like how many, because it's federated learning, right? Like how many kind of endpoints did you have? Yeah.
Okay, thank you. So in our evaluation, we evaluate 32 to 46 clients with models like VGG, ResNet, this kind of models. So the overall, the summed up encrypted model gradients could be hundreds of gigabytes. Okay.
Got it. And so I guess, so since you had, let's say, you had like 32 clients, did you have like 32 FPGAs, one corresponding to each? Maybe that's the part I'm missing, yeah.
No. Okay, so we didn't employ so many FPGAs. The FPGA only works for the aggregator. Okay, and the clients, they take their traditional ways to compute, to train the machine learning models and encrypt them. Okay.
Thank you. Any more questions? If not, again, let's thank the speakers.
Thank you.
So for our next talk, so the first author, Yang, could not make it to ISCA, so the talk will be given by Joel Emer. Joel is currently a professor at MIT. He's also a distinguished research scientist at NVIDIA. I mean, Joel certainly needs no introduction, to this audience in general and to the machine learning acceleration audience in particular, right? So he's made foundational contributions, starting from the Iris chip to data flow taxonomies, modeling tools like time loop, and more recently, he's been doing a lot of work on understanding and designing efficient sparse tensor algebra accelerators. So of course, reading out Joel's bio itself will take me more than 15 minutes. I don't want to deny you all the privilege of hearing him. So Joel, you can take it away and tell us about Trapezoid. Thanks.
Which is forward. Perfect, thank you. Thank you very much, Tushar. As Tushar said, so this is the work that was largely driven by Yifan Yang, who was co-advised by Daniel Sanchez and myself. The subject of this talk is going to be matrix multiplication, very common application. And we're going to be looking at matrix multiplication largely from the perspective of handling sparsity. So sparsity is the proportion of zeros, or conversely, 1 minus the proportion of zeros is the density. And across a variety of applications, you actually see quite widely varying sparsity. And so on this diagram, we show different applications, and we're going to consider sparsity as sort of falling into 3 large buckets. So dense, where all the values are not 0, mildly sparse, where maybe 1% to 10% of the values are non-zero, and then highly sparse, where anywhere from 0.0001 to 0.01% of the values are non-zero. Now, this is obviously not the first matrix multiply engine, and so what we're going to look at is a few of the existing matrix multiply, matrix times matrix multiply engines, starting with the TPU. Now, TPU is designed for handling dense data. And if we try looking at its performance across a variety of kinds of workloads, we see that, and we're going to represent these as D for dense, and MS for mildly sparse, and HS for highly sparse. We can think of a workload as being a combination of those levels of sparsity. So TPU, which was designed for dense computation, does best, marked in green here, on dense times dense matrix multiplication. The green is going to represent the best accelerator speed for any design. As the accelerator tries different combinations of sparsity, if it's within 2x of the best performance, we mark it yellow, and then as it gets worse and worse, we mark it through orange and red. And so, as might be expected, the TPU starts at green. As the data gets sparser and sparser, its performance compared to other accelerators is relatively worse and worse. So our second example is Sigma, which was co-authored by your session chair. The Sigma accelerator was designed primarily for moderately or mildly sparse computations. So if we look at its chart for different kinds of mixtures of sparsity, what you see is it's best at mildly sparse times dense computations. Nearby, it's pretty good, but as the data gets more and more sparse, it falls into the red zone. And finally, another design by your, co-authored by your session moderator, is Flexagon. And Flexagon appears to have been designed primarily for handling highly sparse computation. So if we look at its temperature chart, we see for highly sparse times highly sparse computations, it does very well. But as the density increases, it's further and further away from the optimal design. Now, obviously, from a commercial standpoint, companies don't want to have different designs for every scenario. Every design is very expensive. They would like a design that covers a wide range of workload characteristics. That's the objective of our research here, which we call Trapezoid. And so if we look at the color diagram of Trapezoid, we see it does best in the middle here, but it doesn't fall off too badly at the extremes. So let's going to go into, okay, what is the differentiation as a function of sparsity of these different designs? At a high level, the sparsity is affected by a number of factors. If you've been following the deep neural network accelerator literature, I would hope that you're aware that picking the data flow is an important characteristic for determining the performance of your accelerator. So the first characteristic of the architecture that is influenced by how well it handles a particular level of sparsity is the data flow. Second is, how is the data represented? And it could be in a variety of different ways, which will affect the size of the data and how much data you have to move. And finally, the intrinsics of the hardware architecture, which is largely manifest in how does the design orchestrate data movement? How does it move data? How does it store data? And that determines how efficient it is in a particular scenario. So the idea of Trapezoid is to be able to support several different combinations in order to cover these combinations or these variety of sparsity ranges. However, you need to be parsimonious. You need to be cheap in terms of the amount of extra hardware you're going to add to do that. So Trapezoid is going to try and do this with low area overhead. Okay, let's dive a little bit deeper into how these data flows affect the performance in the face of sparsity. For matrix multiplication, very generally, there are three major data flows that exist. The first one is often referred to as inner product data flow or output stationary. And in this somewhat abstract diagram, we're looking at a diagram where the red rectangle is showing what's happening in parallel, and in output stationary or inner product, you're going to look at a row, which I'm sometimes going to refer to generically as a fiber, is combined with a column, which is another fiber of the A tensor, starting at the A tensor, going to the B tensor, and you're going to do a dot product, which means find the intersecting values in each of those two fibers, and then multiply those values together, sum the results, and that's going to all contribute to one output. So if we have mildly sparse data, it means that when you do that intersection, finding the common coordinates in those two fibers, it's going to be pretty efficient because you're going to get a lot of work to do and you're in a good place. However, as the data becomes highly sparse, now I started to move a lot of data to find out that none of it is going to be useful. All of it is going to be ineffectual computations. Another type of data flow is outer product data flow. This was popular in a number of matrix multiply engines. In this case, you take a vertical fiber of the A matrix, and every combination of vertical fiber of the A matrix and horizontal fiber of the B matrix do a Cartesian product, creating a partial output matrix. And then for each of those combinations, you're going to create a separate output matrix, and those need to then be reduced together. They need to be combined together. So in general, what people found is that actually that complex partial result accumulation make these, not optimal designs. And so I'm not going to consider outer product anymore. The third type of data flow is the Gustafson data flow, also often referred to as a row-wise data flow, because what it does is when it's looking at a horizontal or row of the A matrix, it needs to scale a corresponding row fiber of the B matrix. It scales them and then adds together the results, creating a row of the output. And so this tends to be a very effective, for dense computations, because you need to get a row of the B tensor, P matrix, for every element of the A matrix. It tends to have very complicated and very heavy memory traffic on B. So it's actually not a very good data flow for mildly sparse computations. However, as the sparsity increases, when you have a highly sparse matrices, it turns out that this is going to be the lowest memory traffic. And so this design is going to be good for highly sparse. To summarize this, the inner product data flows are good for mildly sparse, and Gustafson is good for highly sparse computations. And so what you see in those designs that I presented before, TPU and sigma are both based on inner product data flows. And gamma, which is some other work that you might be familiar with, is a multiplier that works on highly sparse computation, as is flexagon. Now, flexagon also can support these other two data flows. So why am I not done? It was because data flow was only one of the characteristics that we needed to look at. Okay. So the other thing that you have to look at is the data representation. TPU used an uncompressed representation holding all the data. However, if you have sparse data, you might like to use a bit mask, where you have a bit that signifies each value that's there. For mildly sparse data, that's highly efficient. If the data is highly sparse, you have a huge number of zeros in the bit mask, so not a very good situation. So if your data is highly sparse, you often like to use a representation like compressed sparse row, where you have a coordinate and value pair for each for each value. This is good for coordinates. This is bad for mildly sparse because the coordinates are large. This is good for highly sparse. And so you want to do bit mask for medium sparse, which is what sigma does, and CSR for highly sparse, which is flexagon. However, the right architecture also changes with sparsity. The TPU is based on a nice 2D PE array. I don't know what's going on with that. That means I'm in questions? Okay. All right, 2D array. Sigma extended that with some data orchestration networks. Good thing about this array is I can get very high compute throughput. Flexagon, because it needed to be actually more efficient in the data orchestration, uses a crossbar and caches and a relatively small number of PEs. So I have reduced data movement there, but it has a small number of multipliers. So I have low compute throughput, and it's not scalable. But if I think about that other array, it is easily extensible. And so what Trapezoid does is extends that 2D array with support for medium sparsity and high sparsity data. So the overview of Trapezoid is for dense computation. It uses an inner product data flow. For medium sparse, it extends that inner product with more sophisticated intersection to be able to pick up larger chunks of data. For highly sparse against not so highly sparse, it uses a Gustafson-based serial computation, but if the data is totally sparse, that is spatial, and if the data is highly sparse, it uses another Gustafson-based data flow. It uses multiple representations depending upon the data type, and so the idea is to support a limited number of data flows and data representations, high efficiency for each sparsity ratio, sufficient to cover the entire range of sparsity. I'm going to jump through the details of the data flows. These are things that are expressed in detail in the paper. I'm just going to show you a summary at the very end. So we did an evaluation, and this becomes a quantitative evaluation of the qualitative one that I showed before. Here's TPU doing very well on dense. Here's sigma doing very well on medium. Here's Flexagon doing very well on highly sparse. And Trapezoid sort of does well across the range. I'm going to skip to conclusion. Trapezoid is the first accelerator that achieves high performance across a wide range of sparsities. It uses 4 distinct data flows, 2 data representations, and a hardware architecture based on a 2D array. It does well. Thank you.
So yeah, I think in the interest of time, maybe, so let me ask a question. Joel, so since it is a 2D array, maybe kind of wearing your NVIDIA hat as well, do you think something like this could become like a potential tensor core inside a GPU, right?
Oh,
Given
I can't answer. It would be nice, but I can't talk about what
it might
future NVIDIA products might do.
Okay. Any more questions? If not, again, please feel free to find Joel after. Thank you. All right, let's move on to the next talk. So we again have a case where the first author actually could not make it to ISCA, so we have another talk from a professor. So José Luis Abellán, he's a distinguished tenure-track associate professor at the University of Murcia in Spain since Jan 2023. Before that, he was an associate professor at UCAM University in Spain for 8 years. He received his PhD from the University of Murcia in 2012, and then he was a postdoc researcher at Boston University for 2 years. So his research interests include architectural enhancements of the GPU systems, the design of customized accelerators targeting both ML workloads and fully homomorphic encryption primitives. He was also, in fact, one of the co-authors of the Flexagon work that Joel just talked about. So Luis is going to tell us about NeuraChip, which is accelerating GNN computations with hash-based decoupled spatial accelerators. Take it away.
Okay, good afternoon. Thank you very much for the introduction. Okay, so I'm going to present this work on behalf of Shivdikar, who was a PhD student that led this work under the supervision of Professor Kaeli. So regarding the structure overview of our presentation, so first of all, what I'm going to do is to highlight what are the key bottlenecks of GNN workloads that motivate the need for the new accelerator, what is called NeuraChip. So I'm going to present what are the 3 key ideas that revolve around this new accelerator. Then I'm going to present some experimental results. And finally, I'm going to give you some conclusions. So GNN workloads, as you all know, works with graphs as input. So there are different varieties of GNN models. But in general, for example, this is a layer of a GCN model. Consists of two different stages, what is the aggregation stage and the combination stage. So basically, this involves matrix-matrix multiplications. They can be sparse, they can be dense. So it motivates different challenges in order to perform efficiently the operations so that we can achieve runtime or even high performance and energy efficiency when running these workloads. No matter what kind of type of matrices are involved there, typically, in order to multiply matrices, we have these two different phases. We have multiplication, and also we have accumulation, merging, reduction. So typically, this has been implemented by different types of data flows. So Emer has explained very properly what are the different data flows that are involved in running, multiplying this kind of matrix, sparse matrix, dense matrices. Respect to the accumulation phase, also, there are many implementations, many kind of accelerators that are based on reduction, tree-based reductions, hash-based, heap-based. So the idea is that the accumulations must happen on chip. Otherwise, it will be very costly accessing of chip in order to retrieve data for accumulation. So our accelerator, as I mentioned, revolves on three key ideas. For that, we are going to leverage the best in terms of, and I'm going to give an example regarding sparse matrix multiplication, which is the Gustafson data flow, row-wise data flow. Also, we are going to leverage hash-based in order to do accumulation efficiently. And finally, we are going to maximize the on-chip accumulation in order to avoid costly memory accesses. So in more detail regarding the main problems on GNN workloads, and looking into the matrix multiplication, matrix-matrix multiplications, so typically accelerators, what does is to combine these two, multiplication and accumulation, in single engines. But this mapping we proved that this mapping is inefficient, basically because there is a diverse data access patterns for each of these two operations. So first, multiplications, the data need to be fetched typically from memory. Then the accumulation happens on chip after computing the partial product. So this on-chip accumulation also depends on what is the sparsity levels in the matrices that could lead to irregular distribution of the task involved in accumulation. Also, the partial products can lead to some cache pollution on chip memory, cache pollution, and also spilling to main memory because you can accommodate most of them on chip, and then there is this situation. So in order to address these major challenges, we have proposed NeuraChip. It is a decoupled spatial accelerator that is tailored to each specific operation, multiplication and accumulation, due to these diverse data access patterns. It is not an unified engine. On the other hand, in order to achieve a load balancing scenario for both multiplication and accumulations, we have proposed a dynamic receding hash-based mapping, DRHM for short, that basically perform accumulation that is totally sparsity aware. On the other hand, in order to address the excessive memory bloating problem, so first of all, we are going to deal with the Agostini data flow, which is very good at it. And we have proposed a tiled version of it that maximizes performance and reuse and data reuse. And on the other hand, in order to avoid cache pollution and memory spilling, so we have proposed a rolling eviction strategy. At the very high level, we have NeuraChip, which is composed of these two engines. So we have, on the one hand, NeuraCores, and on the other hand, we have NeuraMEMS. So NeuraCores, in addition to other kind of operations, they support matrix multiplications in the sense that they compute multiplications. They fetch operands from main memory. On the other hand, NeuraMEMS compute the accumulations and supports a special instruction which is called hash accumulate, or hack for short, and fetch operands from NeuraCores. In a little bit more of detail, in order to compute this MMH X instruction, I'm going to give you an example of X being equal to 4. What does it mean? So essentially, this is how we compute, how we have extended the Gustafson algorithm in order to do the operations of matrix multiplication, where basically, in this case, 4 means the number of non-zero elements from the first matrix in a single column, and then the corresponding raw index in the B matrix, in the feature matrix, we also fetch up to 4 non-zero elements. These 8 non-zero elements are multiplied according to Gustafson algorithm and generate 16 partial products for the MMH4 instruction. Each of these instructions that are basically store partial products need to be sent for accumulation onto the NeuraMem units. In order to achieve an even distribution of these hack instructions to be processed by the NeuraMem units, we have implemented a new mapping algorithm, which is the DRHM. So each of these partial products are called also hack instructions, will arrive to each NeuraMem units according to the DRHM algorithm. So each hack instruction consists basically of data, which is a partial product, the tag, in order to identify uniquely which is the final value that needs to be accumulated in the output matrix for this particular partial product. And what is new is a rolling eviction counter with this CTRR in the mid. So basically, this counter stores how many accumulations, how many partial accumulations are needed in order to compute a partial product, the accumulation of the partial product for a particular value, output value. So each of these hack instructions arrives at this NeuraMem unit, and the NeuraMems receive them. We have implemented a hashing strategy in order to achieve very fast lookups of these partial products that need to be accumulated into the NeuraMem units. So if there is a match, that means between the input hack instruction tag with the one that is stored in the hash engine in a particular memory, in chip memory, which is called hashpath. So you do the accumulation. The counter is decremented by 1, and once it becomes 0, so the partial product has been fully accumulated, so we can store it in memory. At the very high level, this is NeuraChip. So NeuraChip consists of a grid of NeuraCores, NeuraMems interconnected by using a special topology, which is based on a 2D torus, as we saw in there. And this is just a cluster or a tile that is attached to a particular through a particular memory controller to a memory channel, assuming HBM technology. NeuraChip consists of each of these tiles. The data flow in order to execute our matrix multiplications in NeuraChip is as follows. First, there are these MMH4 instructions that arise at the dispatcher. The dispatcher dispatches following a round-robin algorithm through across all the NeuraCores and select one of the NeuraCores as target for performing this matrix MMH4 instruction. Remember that MMH4 requires 8 input elements. So NeuraCore sends the request to the memory controller to retrieve those 8 elements. Once they arrive to the NeuraCore generates the partial product, these 16 partial products, and they are sent according to the DRHM mapping algorithm to the specific NeuraMem units for accumulation. Once the NeuraMem units accumulate all the partial products for a particular output value, then they are sent to memory. Regarding the DRHM algorithm, mapping algorithm, so we have tested different implementation in order to maximize what is the workload, the maximum workload distribution of all this accumulation across all NeuraMem units available in the NeuraChip. So for us, the best implementation is performing hashing of the tag, which is basically the address of the output value for the elements of matrix C for these partial products that need to be accumulated. And we have performing lower bit hashing, higher bit hashing. The best strategy for us was lower bit hashing. And the idea, and this is the word of dynamic that is in the title of the slide, is that in order to achieve a sparsity agnostic mapping of this accumulation, we have a sheet which is represented by gamma. And this gamma is initialized for every new raw index, so that we achieve basically a mapping scheme as follows. So this is without DRHM, that depending on the sparsity level of the input matrices, we have a mapping between the partial products that generate neural core to NeuraMEMS, creating hotspots. In our case, with DRHM, we achieve this. This is basically pretty close to random mapping, which is totally inefficient if we want to implement that. But we achieve very close to that. Then regarding experimental results, so besides the NeuraChip idea and design, we have also developed a new simulator, which is NeuraSim. NeuraSim has been open sourced. There is a link in the last slide where you can download it and you can work with it. And we have two sets of experiments in order to test the improvement of our NeuraChip design regarding the state of the art. First, regarding SP gems workloads. So basically, we have compared respect to CPU, GPU implementations, high-end implementations, and also the state-of-the-art accelerators, other space, Spark, which are for other product, Gamma, which is for Gustafsson algorithm, and we outperform all of them. The particular details about that are on the paper. Then regarding GCN workloads experiments, we also have tested our NeuraChip accelerator against the state-of-the-art, and we have achieved also significant improvement in performance, because basically these accelerators, the state-of-the-art accelerators, are not able to uniformly distribute the workloads. It generates cache pollution in order to store these intermediate results without the rolling eviction strategy that we propose. And also, there is a problem in which when you segregate the computation according to the high-level aggregation and combination phases of GCN workloads, this can lead to inefficient pipeline stalls because this is a very high level. Finally, as a conclusion, so there are diverse data access patterns in multiplications and accumulations. So that's why we have proposed our segregated, decoupled pipeline in NeuraChip in order to compute that efficiently, and we have proved that. In order to maximize hardware utilization, we have proposed our dynamic DRHM mapping scheme in order to do accumulations. Besides, also, in order to generate the partial products, we have mapped in round robin all the different partial product operations across all neural cores. In order to mitigate the memory bloat problem, we have also proposed our rolling eviction strategy that proves very effective. And finally, as I've shown, there are significant speed ups. We also have tested, and we have also many experiments regarding performance, performance per watt efficiency, performance per area efficiency, and other results in the paper. So please access and read it. Finally, this is the NeuraSim simulator is available. We have also the live demo in order that you can configure with different data sets and run and explore our NeuraChip. And thank you very much for your attention. Please, questions?
Hi, this is Mingyu from Tsinghua University. So very nice talk and very solid work. So I'm not sure if I exactly follow the hash part of the work. So you mentioned like you have like higher bits and lower bits hash, and then the lower bit hashing is better. So is this basically the same thing as like the set associative cache, that you have the tag, the lower bit of the address as the hashing, and then you have a tag? Is there any difference here?
Okay, thank you very much. Very good question. So essentially, there are two types of hashing that we apply. So the most novel is the one that is based on the DRHM algorithm, that basically, no matter what are your sparsity levels in your input matrices, in order to do the accumulation of the partial products that heavily depends on the sparsity levels of the sparse matrices. So they send the hack instructions with basically the accumulation to the NeuraMEM units according to this hash-based procedure. Okay. This is one thing. Then, once the hack instructions arrive onto these NeuraMEM units for accumulation, there is another level of hashing that we apply, basically in order to achieve very high, efficient, just constant time of finding the tags that match with the input hack instruction, so that once there is when it's a tag that matches with the input instruction, it means that this is a partial product that has been stored in our NeuraMEM unit that it needs to be accumulated with the new one that is required for final computation of the output matrix for this particular element.
So just in short, it's like you add more like adaptivity or like dynamic into the design, right? Is that correct?
I didn't catch your question, sorry.
So I mean, like in short, is basically you add more adaptivity and more dynamic like behavior in your design.
Absolutely.
Right? Okay.
Yeah,
Cool.
yeah, we have observed that there are problems regarding to load balancing, when especially considering sparse matrix multiplications, and also the two different stages of GCN workloads, aggregation and combination, that combines different level of sparsity. And this way proves very effective in order to achieve load balances so that there are not poor hardware utilization across all the processing elements inside our accelerator.
Okay, thank you. Thank you very much.
Any more questions? So I have one, Jose Luis. So I'm curious about, so when you're mapping GNNs, can you actually map like kind of combination and aggregation in an interleaved manner versus kind of in a pipeline manner, right? Like, so on the chip here, yeah.
Yes, actually. So this kind of fusion schemes that could be very important in order to achieve, to avoid costly of-chip memory accesses could also be part of that. So we can segregate these operations independently, but we have not explored in detail these kind of fusion strategies, but our accelerator can support this kind of strategy in the future, and in fact, this is something that we are going to consider.
So if there's no more questions, let's thank the speaker once again. So thank you all. This concludes this session, and yeah, enjoy the rest of the conference.